Okay, these notes that I have here are going to be the ones that you'll need for section 3.9. In this section, we're going to talk about related rates, and in a typical story problem, I guess, for problems that are in this section, usually you have several things changing in the problem, but also there's going to be a relationship between how those rates are changing in the problem as well. Okay, so let's take a look at problem 1. When a pebble is dropped into a calm pond, ripples are made in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, now in this problem, we got lots of things going on, right? We have a circle of radius r, and the area of the circle is getting bigger. Well, also the radius of the circle is getting bigger, right? But their rates are also changing as well. Okay, the rate of change of the radius is 1 foot per second. Well, that's going to have a corresponding rate of change of the total area of the circle as well. Okay, now what's given in this problem is I'm going to have to do something with area of a circle. Area of a circle is pi times radius squared. The radius is changing with respect to time at a constant rate of 1 foot per second. Okay, now the common notation that you'll see in this section is going to be the Leibniz notation. I'm going to talk more about that after we've done a couple of problems here. But how the radius is changing with respect to time, t, is 1 foot per second, or dr dt is 1, we'll say. Now we want to find how the total area of the disturbed water is changing, or what rate is the total area of the disturbed water changing, when specifically the radius is 4 feet. So we want to find the change in the area of this circle with respect to time, or what we'll call dA dt, at the time when the radius is 4 feet. Okay, now how all these problems are going to go is you're going to set up an equation representing the situation that you've read. You're going to differentiate all variables implicitly with respect to time, and then you're going to be solving for a rate. Okay, so in this problem, I'm working with area of a circle. Area of a circle is pi times the radius squared. Let's go ahead and differentiate both sides. We're differentiating all variables with respect to time t. So now implicitly means that you have to apply the chain rule. Okay, so the derivative of a with respect to time t would be dA dt. On the right, r is the variable. You're going to use the power rule, right? Bring the power down, reduce the power by 1, but then you got to finish by using the chain rule there. Okay, and so you'd want to multiply this by dr dt. Now dr dt is 1, r is 4. I want to find the rate of change for the total area, or that is dA dt. So I'll plug in my known information here in order to get that rate. R is 4, I said, dr dt is 1. So we get 8 pi square feet per second, or in decimal form if you go nearest 2 digits, it's roughly 25.13 feet squared per second is how the total area is changing at this exact moment in time when the radius is 4 feet. Okay. Let's take a look at another problem here. Problem 2. Air is being pumped into a spherical balloon so that its volume increases at a rate of 4.5 cubic feet per minute. How fast is the radius of the balloon increasing when the diameter is 4 feet? Okay, if the diameter is 4 feet, the radius would be 2 feet. Well, the fact that they described volume and how that's changing would indicate that I'd want to begin the problem by working with volume of a sphere. The volume of any sphere, V, is 4/3 pi r cubed. Okay, and that's going to be my general formula here. And I'm going to have to differentiate all variables with respect to time t. Now, one of the things that I usually do early on, after I've got the equation built, is I identify what is known to me and what do I need to find. Okay, So the volume is increasing at a rate of 4.5 cubic feet per minute. They're telling me dV dt. They're telling me how the volume is changing over time. So dV dt is 4.5. How fast is the radius of the balloon increasing? Well, that's going to be dr dt when the radius is 2 feet. R is 2. Okay, so let's go ahead and differentiate this equation here on both sides. You're differentiating all variables with respect to time t. So you're going to have dV dt equals, the power. Use the power rule here on the right, bring the power down. The 3's will cancel there. You'll have 4 pi r squared times dr dt. Okay. Of course, since you're using implicit differentiation here with respect to time, make sure that you finish differentiating by using the chain rule. Some students won't do that. Okay. Now I need to find dr dt, right? So let's go ahead and solve this equation for dr dt. I'm going to divide both sides by 4 pi r squared, and then I'm going to plug in my information here that I'm given. The volume is changing at a rate of 4.5 cubic feet per minute, so dV dt is 4.5. R is 2. Okay. Well, in the denominator, you're going to have 16 pi. 4.5 divided by 16 pi. If you were to multiply the top and bottom by 2, you'd have 9 divided by 32 pi. Only reason why I'm doing that is to get rid of the decimal that was in the numerator. You didn't need to do that, okay? You could have left it in the form 4.5 divided by 16 pi. That would have been the exact answer. In decimal form, it would be roughly 0.0895 feet per minute. Be sure that the units are included in your answer. Okay, that's something that I'll be looking for when I grade, whether it's feet squared per second or feet per minute or, centimeters per second or whatever the deal is. Okay, make sure that that is included. Also, of course, pay attention to where the book would like you to round. Okay, and if they don't say anything about rounding, I wouldn't care where you round, although be sure that you still know the exact answer. Okay. Now, let's take a look at, so in this problem, this spherical balloon is being blown up, so the volume is changing, right? But that's not the only thing that's changing in the problem. The radius is also changing. I mean, you can look at several things changing in this problem, like the radius is changing. Okay, the radius is increasing. Now those rates are related, right? How the radius is increasing has an effect on how the total volume is increasing. Okay, so there's a relationship between those rates there. Let's take a look at another problem. Okay, problem 3 says that a ladder that is 25 feet long rests against a vertical wall. The bottom of the ladder slides away from the wall at a rate of 2 feet per second. Part A, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 7 feet from the wall? Okay, let's draw a picture of what's going on here. So I have the ground and then the wall, and then there's a 25-foot ladder leaning against the wall there. It's a vertical wall, right? So I'm going to be working with a right angle. And I've formed a right triangle here. I'm going to call the distance from the wall to the base of the ladder X, and I'll call the distance from the ground to the top of the ladder Y. Now the bottom of the ladder is sliding away from the wall at a rate of 2 feet per second. X, therefore, is changing. X is getting bigger as time goes on. So in this statement here, they're essentially telling me that dx dt is 2 feet per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 7 feet from the wall? Okay, so the thing that we need to find here is how y is changing. We need to find dy dt at the moment in time when x is 7 feet. Okay, well, In this picture, I've got a right triangle, and so I can use the Pythagorean theorem. The sum of the squares of the legs equal the square of the hypotenuse. Or for us, that's going to be x squared plus y squared equal 25 squared. So here's the equation that I have to work with, and now I'm going to differentiate both sides with respect to time t. Let me do that now. So that you're going to have the derivative of x squared with respect to time t would be 2x dx dt, and then plus derivative of y squared with respect to time t would be 2y dy dt. Derivative of constant is always 0. Okay, now we want to find dy dt when x is 7. So let me solve this equation for dy dt. I'm going to subtract 2x dx dt from both sides and then divide by 2y. The 2's will cancel, and that's going to leave me with negative x over y times dx dt. Okay, dx dt is 2, x is 7. So I just need to find y here, and then I can know dy dt. Well, to get y, I can use the Pythagorean theorem again. If x is 7, and the hypotenuse of this triangle is 25, then the height of the triangle would be 24. Okay, so in other words, 7 squared plus 24 squared would be 25 squared. You can do a side calculation in getting that. Y is 24. And so now I have all my information here to get dy dt. 2 over 24 is 1 over 12. Negative 7 over 12 feet per second would be my answer. A couple things. So again, make sure that the units are included. If they are not included, you won't get full credit. Okay, because I'll have people write down the wrong units. All of them just write seconds or feet or something like that, or something that's not even close. Now, another thing that you'll notice here is that we got a negative value. What that means is that in this problem, y is getting smaller. Now, I mentioned that x is getting bigger, right? As the ladder is sliding down the wall, the bottom is pulling away from the wall, and so x is increasing. If you have a positive rate, that means that the variable is getting bigger over time. If you have a negative rate, that means that the variable is getting smaller over time. Okay, so these two answers up here were positive. That's because, in this first problem, the area of the circle was getting bigger over time. In this problem, the radius was getting bigger over time. Now, if this number here were a positive, that would mean that y is getting bigger over time. Well, that's not happening, right? So nobody's pushing the bottom of the ladder towards the wall to make y get bigger. Okay, so one of the things that I'd like you to observe early on is your answer and whether or not that's going to be a positive or a negative number. Okay, like the fact that I need to find dy dt, and I know that y is going to be getting smaller, means that before I did anything here, I could know that my answer is going to be a negative. Okay, so look for that. And of course, a mistake I'll see sometimes students make is they won't have a negative when it should be a negative. Okay, so make sure that you're aware of that. Now, another thing is that going back to the notation, I mentioned that we're going to be using Leibniz notation for every single one of these problems. Okay, I wouldn't want to say y prime. Okay, because y could be mistaken as a function of x. And I'm not wanting to find dy dx, right? I'm wanting to find how y is changing with respect to time. So because time is the variable here that we're interested in with all the other variables, we want to use Leibniz notation and indicate that this is with respect to time t. Okay, so take note of that. You're not going to find, y prime or v prime or r prime or a prime or something like that in any of the problems in this section. Okay, because it can be misleading then. What variable are you talking about if you're using the the y prime notation. Another thing that I would highly recommend is for these problems, draw a picture. Okay, especially if you're a visual learner, draw a picture. It helps you, the idea is that it can help you get organized with your thoughts and hopefully get the correct equation written in order to solve. All right, let's take a look at part B. Find the rate at which the angle between the ladder and the wall is changing when the bottom of the ladder is 7 feet from the wall. Okay, so here's my picture, redrawn, and I'm interested in the angle between the ladder and the wall. I'll call that angle theta, and how that angle is changing with respect to time. So in this problem, I can know right away that I'm wanting to find d theta dt. How is this angle changing with respect to time t? Now, another thing that I can observe early on here is that as the ladder is sliding down the wall, theta is going to be getting bigger. So d theta dt is going to be a positive number. Well, let's see here. So I know dx dt is 2. X is opposite theta. I also know the hypotenuse of the triangle. That's 25 feet, right? Okay, so opposite over hypotenuse, that'd be how we define sine theta. Anytime you're working with angles, also early on you should be thinking of trig stuff. Sine theta is opposite over hypotenuse. So sine theta would be x over 25. Now that I've got my equation, I can differentiate both sides with respect to time t. And so let's do that. The derivative of sine theta with respect to time would be cosine theta d theta dt equals derivative of x over 25 with respect to time would be 1 over 25 dx dt. dx dt is 2. So you're going to have 2 over 25 on the right. Now we wanted to find d theta dt, right? Find the rate at which the angle of the between the ladder and the wall is changing. Well, let's divide both sides by cosine theta. So you're going to have d theta dt all alone now. And on the right, you're going to have 2 divided by 25 cosine theta. Well, cosine theta, that'd be adjacent over hypotenuse. The adjacent side is y, and at this moment in time when the ladder is 7 feet from the wall, the base of the ladder, y is 24. Okay, so 24 over 25, that would be the value of cosine theta. The 25s will cancel, and that's going to leave me with 2 over 24, or 1 over 12 radians per second, then would be the units there. When you're working with angle measurements, assume that you're in a radian measure, unless you're told otherwise. Okay, so radians per second would be the units. Now, another way that I could have worked this problem is, in part A, I was finding dy dt. So I could have set this up in terms of cosine theta, okay, since I knew dy dt. Now, if I didn't have this information known, then what you see here would be the better option. Otherwise, I would have to find dy dt. Okay. Another option that you could take is you could work with tan theta. Tan theta is opposite over adjacent, but if we had tan theta equal x over y, then we would have to use the quotient rule and we would have to know dx dt and dy dt. Well, we know those values, but the quotient rule makes this problem more difficult than it needs to be. You'd still get the same answer, okay? It's just you're making it more difficult than what it needs to be. Okay, so obviously when setting up the problem, consider that, we want to get the answer as, using the easiest possible option that is there. Now, one mistake that I will see way more than I should with problems like this is that students will want to substitute values into the equation too early. Okay, like if I go back to part A, x is 7 and y is 24. Like I could find that, first thing if I wanted to. X is 7, y is 24 by using the Pythagorean theorem. But I wouldn't want to replace 7 in for x until I have differentiated. If I were to have placed 7 in for x and then differentiated, I would have dy dt equals 0 divided by 2y, or dy dt would be 0. Okay, 0 is not the answer, right? Y is shrinking, okay, and so y would be, a dy dt would be a negative number. Be careful about that. I see that too much, okay? And that's a note that I have on the next page here. Substituting the known values of a variable before differentiating will lead to an incorrect answer all the time, okay? Be sure that you first use the chain rule to implicitly differentiate both sides with respect to time t, okay? Don't plug anything in until you've taken a derivative on both sides with respect to time t, right? We'll go ahead and stop here.